This presentation is on absolute geometry, and the presenters are Carrie Hadfield, Pfeiffer Harala, and Sherry Mays. In a land far, far away, over 2,000 years ago, there was a great Greek mathematician, Euclid of Alexandria, the father of geometry. Little did Euclid know, he started an epic battle between mathematicians that would continue for centuries. It all began with Euclid's book, Elements, written in 300 BC. Elements is made up of 13 books and begins with 23 definitions, 5 postulates, and 5 common notions. The topics covered in the books include triangles, rectangles, circles, polygons, proportions, similarity, number theory, solid geometry, pyramids, and Platonic solids. In absolute geometry, the 5 postulates are what interest us. Here are Euclid's 5 postulates. We will take a look at each one of them individually. The first postulate. It is possible to draw a straight line from any point to another point. The first postulate focuses on the idea of straightness. Given any 2 points, the connection between those points is created by a straight line. Conversely, if you were to draw lines like this, you are able to connect the points, but those lines are not straight. This is what the first postulate prevents. Instead, you must draw a line as such. Creating a straight line between 2 given points. The second postulate. It is possible to produce a finite straight line continuously in a straight line. The idea of flatness is the focus of Euclid's second postulate. It states that you cannot draw a line that has bumps in it, such as this. A line will remain flat at all times, guaranteeing flatness. The third postulate. It is possible to describe a circle with any center and radius. The fourth postulate. All right angles are equal to one another. The fourth is also uncontroversial and states simply that all right angles are equal, a proposition necessary to ensure that the space we are working in is essentially the same everywhere. This property of sameness at every point is the defining quality of a geometry. For mathematically speaking, there are wilder and more unruly spaces. It does not matter what object you use or where the object is located. All right angles are equal to one another. For example, we can talk about right angles in France, Germany, and Colombia.
Ok, bonjour, je vais expliquer en français. Ça, c'est un angle droit. Un angle droit à 90 degrés.
Hier ist ein deutsches Buch. Und ein deutsches Buch ist immer ein rechter Winkel. Hier, schau mal. Hier ist ein rechter Winkel. Ein rechter Winkel hat immer 90 Grad. 90 Grad ist immer ein rechter Winkel.
En español, Este es un ángulo recto. Un ángulo recto es un ángulo perfecto que siempre mide 90 grados. Podemos tener 4 ángulos rectos en el libro de español.
Again, all right angles are right angles.
Finally, the fifth postulate. If a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if they're produced indefinitely, will meet on that side on which the angles which are less than two right angles. This is where things get dicey. There is a lot of controversy over this postulate. It stems from the fact that Euclid himself struggled with the fifth postulate and was never able to formally prove it. This postulate is what is now known as the parallel postulate. Quoting Wolfram MathWorld, Euclid's fifth postulate cannot be proven as a theorem, although this was attempted by many people. Euclid himself used only the first 4 postulates, which is now known as absolute geometry, for the first 28 propositions of the elements, but was forced to invoke the parallel postulate on the 29th. In 1823, Janos Bolyai and Nikolai Lobachevsky independently realized that entirely self-consistent, non-Euclidean geometries could be created in which the parallel postulate did not hold. Gauss had also discovered but suppressed the existence of non-Euclidean geometries. Other noteworthy mathematicians that have tried to prove it include Ptolemy in the 1st century AD, John Wallis in the 17th century, and Girolamo Saccheri in 1733. From all the arguing came what has been called absolute or neutral geometry. The term absolute geometry is credited to Janos Bolyai in 1832. Bolyai considered one of the founders of non-Euclidean geometry. Non-Euclidean geometry is a geometry that differs from Euclidean geometry in its definition of parallel lines. The term absolute being chosen because this geometry is seen as being free from imperfection, that imperfection being Euclid's fifth postulate. The use of neutral came about because scholars felt that this geometry was not taking sides on the parallel postulate issue. It was remaining neutral on that point. Again, in Euclid's Elements, the first 28 propositions and proposition 31 avoid using the parallel postulate and therefore are valid in absolute geometry. Absolute geometry is the geometry created by using only the first 4 postulates and taking no stand on the fifth postulate or on parallel lines. These postulates were all that were used to define geometry for over 2,000 years. In the winter term of 1898 to 1899, David Hilbert constructed a logically complete geometry. To do so required 21 axioms. Those 21 axioms are contained in his book, Grundlagen der Geometrie, which was first published in 1899. It was later translated into English under the title Foundations of Geometry in 1902. This book is considered the second most influential book written about geometry behind Euclid's Elements. In the Foundations of Geometry, Hilbert defined 3 things which he called points, lines, and planes. And he said those things are connected by 3 relations. Incidence, which means on, order, which means betweenness, and congruence. He then went into his 21 axioms, but it was later discovered that he really only had 20 unique axioms since 2 of them were so closely related. If we recall, in Euclid's Elements, Euclid used 23 definitions, 5 postulates, 5 common notions, and 48 propositions. We will now be able to explore why absolute geometry is so important to all the types of geometry we study today.
The geometry that we are talking about is neutral geometry, meaning it's not taking sides. This is why we are using Switzerland as a common theme in our presentation, in the sense that we take no stand on the parallel postulates or on parallel lines, as other geometries do. This allows us to do two things. First, we can see what theorems in Euclidean geometry are independent of the Euclidean parallel postulate, and there are many. That is, we will be able to identify the theorems that can be proven without any reference, and thus without dependence on the Euclidean parallel postulate. Second, it allows us the freedom to impose other parallel postulates, for example, a hyperbolic parallel postulate, and see how the geometry changes as a result. Absolute or neutral geometry builds a foundation for other geometries and lets us better understand the most basic parts behind them. By adding different views of that fifth postulate, dealing with parallel lines, other geometries, including hyperbolic and Euclidean, can be explored. If we take what we have learned from the first four postulates and leave the neutral land of absolute geometry, by taking a stand on the idea that there could be indeed more than one line parallel to any given line through a point not on the line, in fact, infinitely many parallel lines, you will reach the land of hyperbolic geometry. The picture we have shows a hyperbolic plane crocheted, and we see a line, and then we have a point not on the line, and through that point you can see stitched three lines, all of which are parallel to the given line, meaning they will never intersect no matter how far they go. So we can see three lines, and ultimately we could stitch and see there are infinitely many parallel lines parallel to the given line in hyperbolic geometry. In what we have learned from the first four postulates, if we take what we have learned and leave the neutral land of absolute geometry by taking a stand that there could be just one line parallel to any given line through a point not on the line, you will reach the land of Euclidean geometry. We have a given line, we have a point not on the given line, and we have one line exactly that passes through that point parallel to the given line. Spherical geometry we have studied in this course. Spherical geometry does not have absolute geometry as its foundation, because in spherical geometry you could take any two lines, any two great circles, and they will intersect at 2 points. There are no parallel lines in spherical geometry, therefore you cannot take absolute geometry and add something to it and call it spherical geometry. The picture we have shows two great circles intersecting at both point E and point F. So two lines intersecting at 2 points. Another point about absolute geometry is that SAS, side angle side congruence, is a stated axiom. That also allows further proof of angle side angle and side 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 congruence of triangles within absolute geometry. Therefore, Euclidean and hyperbolic geometries, because absolute is their foundation, also have the side angle side congruence, as well as proof of angle side angle and side side side. There are other geometries that do not have side angle side congruence. For instance, taxicab geometry is one of those. And below we have pictured two triangles with side angle side, which then therefore lead into your side 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 or your angle side angle. Thank you for spending time with us learning about absolute geometry, how it is the foundation, basically, that you can add to build to hyperbolic or to Euclidean. And that all came about because Euclid's fifth postulate caused so much upset in the mathematical world that people have spent centuries trying to work through it. And absolute geometry is the answer they have to that. Here are all the resources we used in putting together our presentation. Thank you.